As you watch forces and motion, keep these questions in mind.
What is the relationship between distance, time, and speed?
In what ways do the air resistance and the shape of an object influence its acceleration and speed?
Even though it may not feel like it most of the time, everything on the planet is in a state of constant motion and constantly affected by the physical forces of the universe. What physical forces can you feel?
I feel gravity, of course, every time I walk, jump, run.
Everybody feels like gravity all the time and friction.
So when you rub your hands together, my hands get warm, my palms get warm, and sometimes when I do it really, really fast, they start to sweat.
Rubbing your hands together and creating heat is a form of friction.
You feel friction all the time, just standing still, walking, running, hitting.
Like water resistance when swimming, running, you feel the wind pushing against you.
Pressures, and rising in the atmosphere.
I feel pressure, but it's not like a pin pressure, it's like spread out.
Hello, Jones is my name, and chauffeuring Mrs. Gideon around is my game. And of course, cricket, yes. Well, it's all a matter of distance over time, isn't it? What I'm really talking about, of course, is speed and how to determine it, yes. And you won't go far wrong if you always remember that speed is distance over time.
Speed equals distance over time. A graph helps to calculate your speed. Distance on the vertical axis and time on the horizontal axis.
Starting off, I begin to cover a greater amount of distance in a shorter amount of time. This can be shown as an upwards curve on a graph. That is because my speed is increasing. Eventually, I reach a constant cruising speed, which is never over 50 kilometers an hour. No, never, never over 50. Unless, of course, when it's over 60. Oh, only joking. You can always tell, of course, when you've reached a constant speed because the curve is a straight line. Yes, and you must always keep a very good lookout in case anything untoward should happen. Yeah. Good grief! What do you know? This calls for an emergency stop! Right then, the wonderful thing about making a graph of your journey is, here's my graph, is that at any point along this curve, you can work out your speed. You see, this is the point where I started off. Here's nothing there. I gradually gained speed, and this straight line is my constant speed. Then I slowed up because that little critter jumped down in front of me. Look, there you are. He's squashed on that line there. Or not, as the case may be. Right, what if, for example, I wanted to work out my constant speed? Well, that's this straight line here. All I do is I draw a line from the beginning down to the time axis. There you are. That's the beginning of my constant speed, and then my constant speed ends around about there. There you are. I'll draw another line down. That gives me my time during my constant speed, which 50 minus 20, that's 30 seconds, which of course is half a minute, if you're clever. If I want to find out how far I travelled at a constant speed, I draw another line across here, there we are, goes to 200, and another line, I trace it across, there we are, reach 700, there we go. Right, so in order to find out the distance I travelled at my constant speed, it's 700 minus 200, which of course is 500. And that time there was 30 seconds, that's half a minute. Now, 500 metres is, of course, half a kilometre. 30 seconds is half a minute.
Speed equals distance over time. So that's 500 metres divided by 30 seconds, which is 16.7 metres per second.
So what's that? That's 60 kilometres an hour. Well, we can't all be perfect, can we? Anyway, yes, when that little critter ran out, of course, I slowed to a halt. But, of course, the time was still ticking. So my line carries on, so it's flat. That geezer in the Rolls Royce, right? It was well sorted for time and distance. But from where I'm coming from, it's acceleration that impresses your mates. Oh, yes. And the better you can understand it and illustrate it, the more impressed they'll be. So all I've got to do to get my speed is measure my time between the distance markers. You'll see them as I blast past.
If we measure the slope at different points along the graph, we get Andy's speed at those points. And we end up with a table of speed against time.
Now this is where the clever bit comes in.
If we plot these points on a speed-time graph, speed on the vertical axis and time on the horizontal axis, we can work out acceleration by measuring the gradient of the speed-time graph at any point.
In the manual, it says that my kicking motor does 0 to 90 in 9 seconds. But as you can see, I've synced it up and it does it in 8.5. Nice one. Stopping distance is calculated with your distance time setup. So, if I slam on the anchors at 40 kilometres an hour, let's see what happens.
Although the time taken to stop doesn't change very much, the distance travelled increases dramatically. At 40 kilometres per hour, the car travels 9.8 metres and comes to a stop in 2 seconds. At 80 kilometres per hour, the car travels 25.1 metres and comes to a stop in 2.7 seconds.
Wicked. Oh, hi, Flash Hour is my name. When I'm not making wedges of cash in the city, I'm blatting around on my bike. It's fast, mean and expensive, not unlike myself. Now it's time to see what real acceleration and deceleration are all about. And just in case you think I'm cheating, here's the speedo captured live on camera. Read it and weep. As you can see, the graph's gone completely off the scale. I'm doing about 230 kilometers per hour, and that's legal, at least on a racetrack. The mass of a motorbike compared to a car is much less, and this means that the bike gets started much more quickly. This shows in its acceleration. And apart from smashing the opposition when it comes to acceleration, emergency stops at the same speeds an equivalent car will also prove the bike to be much more efficient. So remember, speed equals distance over time, and you get that from your distance time graph. And time equals money, so I'm out of here. Acceleration is wicked, and you work it out from your speed time graph. If you're planning on making an emergency stop, the faster you're going, the longer distance you'll travel.
Unbelievable stuff. My dream is to fly, and maybe even one day, maybe we could actually land without a parachute. Let's see what the laws of physics have to say about that. Now, if we're going to demonstrate the physics of falling, first, we need someone who's prepared to fall. Second, we need some very technical people. Are they going to make some measurements? And thirdly, we need a stopwatch, which is in the camera. I said first we need someone who's prepared to fall. I see, that's me. Let's see how fast we can go.
How fast was that?
We put several markers on the crane. They're at 10-metre intervals all the way up the crane, so we can help us gauge exactly how low Adrian comes with his jump and how much he returns to. On top of which, we've actually worked out on the calculator exactly, bearing in mind his weight and the stretch of the rope, the same thing.
On the first descent, Adrian takes 4.4 seconds to fall 63 metres. On the second descent, he takes 4.7 seconds to fall 40 metres. And finally, on the third descent, he takes 4.3 seconds to fall 35 metres. Using the formula speed equals distance over time, his average speed on the first descent is 14.3 metres per second. The average speed on the second descent is 8.5 metres per second. Finally, his average speed on the third descent is 8.1 metres per second. So Adrian's average speed depends on the height of his fall. As he falls, he starts to accelerate. So the shorter his fall, the less his top speed. The calculated speed for each descent is the average of his initial speed, which is 0 at the start of the jump, and his top speed. This decreases with each descent.
So the first conclusion is, the higher you jump from, the higher your top speed's going to be. Now, if we want to jump off something very, very high, something extremely tall, and live, we have to find a way to slow ourselves down. So this time, I'm going to jump like a base jumper, like a flying squirrel. Wearing this big suit, I'm going to try and catch all the air I can. Ready, steady, go!
By wearing his suit and jumping like a flying squirrel, Adrian is increasing the air resistance on his body. Air resistance depends on shape. The average speed on his normal jump was 14.3 meters per second. The average speed for his squirrel jump is only 12.6 meters per second. So, his squirrel jump is slower than his normal first jump.
Now, the second conclusion is that I can slow myself down while I'm falling by changing the shape of my body. Now that surely has got to be as wild as it gets.
Did you know bungee jumping was started thousands of years ago by the indigenous people of the South Pacific? They jumped off of bamboo towers with vines tied to their legs.
Modern bungee jumping was started by England's Oxford Dangerous Sports Club in the 1970s. They used a string of small elastic ropes, like the ones you might use to keep luggage on the roof rack of your car.
Top cyclists can reach a speed of 15 meters a second. That's over 55 kilometers an hour. But during a race, the speed will vary. To understand how something gets faster or slower, you need to know about forces. It's forces that change the speed. So what are the forces acting on the bike and its rider? To move forwards, the rider needs to apply a forward force.
3, 2, 1.
She pushes hard on the pedals. This forward force changes the speed of the bike. It accelerates. But the bike doesn't keep going faster and faster forever. Why is it, even though the cyclist keeps pedaling, her speed remains the same? As well as the force pushing the bike forwards, there are counter forces trying to push it back. So what are these counter forces? There's friction between the tires and the track, friction between moving parts on the bike, and the cyclist is pushing against the force of air. Inside the cycle track, the air is still. As the cyclist moves through the air resistance starts to bend the flag. The faster the cyclist goes, the greater the force of air pushing the flag and the rider backwards. So as the cyclist pushes the bike forwards, friction and air resistance are working against it, effectively pushing it back. If the forward force and the backward force balance out, the speed of the bike remains constant. So how can our cyclist change her speed? As she presses harder on the pedals, the forward force is increased. The forward force and the counter force are no longer balanced. so the speed of the bike changes. It accelerates. But again, she doesn't get faster and faster forever. What's happening to the counterforces? There's a small increase in friction and a big increase in the force of air pushing backwards. The faster the bike goes, the greater the counterforces. Eventually, the forces are balanced and the cyclist reaches a new constant speed. To get faster, she's got to keep unbalancing the forward and backward forces. She's got to keep applying a bigger and bigger forward force.
Okay, Yvonne, that's enough now. Warm down. That's very good. Call it a day now. Great.
Racing bikes like these don't have any brakes. Instead, the cyclist simply stops pressing down on the pedals. The forward force is now much smaller. The forces are unbalanced again, so the speed of the bike changes. This time, it gradually slows down. When a skydiver jumps out of a plane at 3,000 meters, her speed goes through some big changes. So what's happening to the forces as you fall through the air? The force of gravity is always trying to pull us towards the Earth. Before the skydiver jumps, the floor of the plane provides a counterforce which balances the downward force of gravity right up until the moment she steps out. Gravity immediately pulls her towards the ground, and she starts to accelerate downwards. But air resistance is acting in the opposite direction. The faster she falls, the greater the air resistance. Eventually, the upward force of the air equals the downward force of gravity. When forces are balanced, the speed remains constant. That doesn't mean she stopped falling. It means she stopped accelerating. She's still doing a steady 55 meters per second, and hitting the ground at this speed isn't a good idea. To slow down, the upward force needs to be greater than the downward force. When the parachutes open, air resistance suddenly becomes much greater than gravity. The forces are no longer balanced, and this changes her speed. She slows down. Because she's slowing down, air resistance decreases until it balances gravity again, and she reaches a much slower constant speed. Approaching the ground at 5 meters per second is a much better idea. As she hits the ground, there's a thumping great counterforce from the Earth, which decelerates her very quickly. So for skydivers to land safely, they need to understand forces and use air resistance to slow themselves down. Gravity's pulling this plane towards the ground. So why doesn't it fall out of the sky? there must be a counterforce pushing upwards. This upward force is called lift. Even a jumbo jet weighing over 300 tons can create enough lift to get off the ground. So how does it work? You can create lift by blowing over the top of a piece of paper. Air particles are bumping into the paper from all sides. These create forces. If the paper isn't moving, the air forces above and below must be balanced. Blowing pushes the air particles over the top of the paper, so fewer particles hit it from above. The downward force is momentarily smaller than the upward force, so the paper rises. For a wing to work, it needs to be able to create lift. So what shape does it need to be? With an asymmetrical wing, the airflow over the top is different than the airflow underneath. The air has to travel further over the top than it does underneath. If it has to travel further in the same amount of time, the air over the top must be traveling faster. We know from our piece of paper that making the airflow faster over the top reduces the downward force. The downward force is smaller than the upward force, so the wing lifts. When a plane goes fast enough, the wings create enough lift for it to take off.
You've been given all the information. Now it's your turn to discuss the questions. Take a moment to talk about the following.
What is the relationship between distance, time, and speed?
In what ways do the air resistance and the shape of an object influence its acceleration and speed?
We hope you've enjoyed this assignment discovery examination of forces and motion.
If you'd like to learn more about what you've just seen, go online or check out these books at your local library.